Hey everyone, today we're going to be looking at the properties of light. In order for us to understand the electron and quantum mechanics, we want to be comfortable with the properties of light. So let's go ahead and get started here. The first thing that I want us to understand is that one of the ways we measure light is using its wavelength. Wavelength is referring to the distance between two corresponding parts of a wave. Remember, the units for distance are meters, so we should be using meters when we look at light. Now, the distance between peaks or troughs on a wave, specifically a light wave, can be very small. So sometimes we'll see nanometers or micrometers. But when we use math, make sure to convert to meters. Frequency is the number of cycles per given time, so quite literally how much the light will go up and down in a given second. A hertz is going to be a unit for per second. So did the light go up and down 5 times per second, 5 million times per second? It really just depends on the type of light that we're looking at. So let's look at a couple examples here. Let's go ahead and look at first a red light. So a red light is fairly unenergetic, and one way we can represent this is with its very long wavelength. So the longer the wavelength, the less energy this light will have. And notice the long distances between peaks. So red light generally will have a larger wavelength. And if we look at something like a blue light, which is more energetic than a red light, we'll notice that the wavelength actually decreases. The distance between two peaks here goes down. So the next thing that I want to consider is we're going to look at the electromagnetic spectrum. But what I want us to consider is how does wavelength relate to frequency? So frequency, notice, is the number of times the light goes up and down in a given second, number of cycles per unit time. And if I shorten this wavelength, if I decrease the distance between two peaks, the amount of times that this light can go up and down, the number of cycles that happens per second, is going to increase. So one of the things that I want us to understand is that frequency and wavelength are actually inversely related. As one goes up, the other goes down. Generally speaking, for any type of energy that moves in waves, frequency, and when you multiply frequency and wavelength, you get the speed at which the wave is traveling. And since really we're only going to be looking at light, the speed of the wave is going to equal the speed of light, which is 3 times 10 to the 8th meters per second. And this constant and equation are given to you on the College Board formula sheet. Now, if you look over on the right-hand side, you will see the electromagnetic spectrum. Notice here we have purple light and red light. So purple or violet light. We're hopefully all very comfortable with Roy G. Biv. Roy G. Biv indicates the order of visible light from lowest to highest energy. One little trick that I like to use, the violet light is next to the ultraviolet. And I've always associated the word ultra with higher energy. So the ultraviolet is near the violet part of the visible spectrum. And infra means below. So it has less or below energy than the red light. Infrared is below red. So that's just one little trick that I like to use when we're thinking about the electromagnetic spectrum. So moving on, the last thing that we want to be comfortable with is understanding how frequency and wavelength are related to the energy of light. And I already kind of started talking about this as in terms of wavelength. If the wavelength increases, the amount of energy for light will decrease. But notice this equation I'm going to provide for you here. E equals h nu. E is the energy of light. Nu is frequency. And h is Planck's constant, which is why we have this excellent picture over on the right-hand side. Planck's constant is a number which was derived for the quantization of light. Really, it's just a number you need to be able to calculate the energy of light given the frequency of a photon. So E equals h nu. H is 6.626 times 10 to the negative 34th joules seconds. And when you multiply h and nu, the seconds will cancel, giving you the units of joules. So one thing that I want to talk about is the photoelectric effect. First off, the photoelectric effect is this phenomenon that occurs, and still occurs, where electrons are ejected from metal when light of a specific frequency shines on it. And notice that I kind of talked about red light having a low energy compared to blue or even green light. The blue and green light are able to eject these electrons, whereas the red light wasn't. It's not energetic enough. And scientists actually had a hard time describing why this was occurring. Um, and until Albert Einstein came around, and he won his first Nobel Prize for this. And what he said was that light has dual wave particle nature, meaning that depending on the situation, light could either behave as a wave or as a particle. Now, the waves are going to be basically behaving as we described them before. They have a wavelength, they have a frequency associated with them. But light can behave as a particle, and we call these particles photons. Photons are massless, volumeless particles, air quote, of energy. And the way that I like to think of photons is that they are the most basic unit of energy. You cannot have a half or a third of a photon. You can only have a whole number of photons. It's the most basic unit or basic form of energy. So the last thing I want to do is I want to practice using the wavelength, energy, and frequency and the equations that I went ahead and showed you today. The question is this: what is the energy of a photon? What is the energy of a photon, given that it has a wavelength of 424 nanometers? So once again, the first thing that we're going to do is convert nanometers to meters. Being comfortable with the conversion for nanometers to meters is actually going to be probably pretty important. There are 10 to the 9th nanometers for every 1 meter. Plug this into your calculator and you'll get 4.24 times 10 raised to the negative 7th meters. We can now take this equation and it asks for the energy, but I'm given the wavelength. So the only equation that I have for energy is going to be E equals H nu. But I don't have nu. I have lambda. I have wavelength. So what I'm going to do first is determine what nu, what frequency is, using the other equation, c equals lambda nu. C I know is the speed of light, 3.00 times 10 to the 8th meters per second. I have the wavelength, which is 4.24 times 10 raised to the negative 7th meters times nu. So I take this whole quantity here and divide it over to get nu is equal to 6.82 times 10 raised to the 14th hertz, or per second, remember. So notice that this per second gets left down below, and 1 over second is quantitatively equal to the hertz value. Now that I have the frequency, I can take that and plug it into the equation up above to find the energy of this light. Let's go ahead and change my color here. And I know that energy is equal to Planck's constant, which is 6.626 times 10 raised to the negative 34th joules seconds. Multiply that by 6.82 times 10 to the 14th hertz, which remember is a per second. So the second and the hertz will end up canceling out, giving me the energy of a photon, which is 4.51 times 10 raised to the negative 19th joules per photon. So this is for a single photon. This is a tiny amount of energy, and that makes sense because a photon is a single particle of energy. So oftentimes we'll convert this to joules per mole. And how do I convert between particles and a mole? That's right, Avogadro's number. So keep that on the back of your mind when you're practicing some of these types of problems. As always, let me know if you guys have any questions. Otherwise, I'll see you later.